All right, so last time we got into this idea that was a little bit radical. These radicals again, and whenever I'm taking the square root of x, we realize you can take it and you can rewrite in terms of the exponential powers. And sometimes it's very, very useful to write radicals in terms of exponents. And in fact, a lot of things you do in mathematics, we do a lot of things not with the square root, the radicals, we do a lot of stuff with the exponentials. And you can take this again and you can adjust it so it's the nth root. So say x to the power of 1 over n. And if you power up the x, you power this up as well. So this is a property that you want to make sure you're very familiar with. And also we talked a little about the graph of the square root function last time. This is one of those base graphs that, yes, you are going to need to memorize this. You're going to need to know this. The domain is going to be all the values to which you can plug in. And things I can plug in, I can see it graphically. It's going to be everything that's going to be non-negative. Because I can plug 0 in because 0 squared is going to be 0. And that's exactly what it talks about whenever I take the square root. You know, if I was going to have 2 squared, that's going to be 4. So the square root of 4 is going to be a value of 2. If it's going to be positive values, that is. Now, another thing real quick is I can also talk about the cube root. And the cube root is going to be real similar. Its graph's going to look a bit more like this. Its domain is going to be all real values, and its range is also going to be all real values. And we can say negative infinity to positive infinity. And you can also talk about the fourth root and the fifth root. But the fourth root is going to look something very similar to what's happening with the square roots. And the fifth root is going to look really similar to what's happening here with the cube root. So if you know these two, you kind of have a good idea what's happening for all the different roots. All right, so we talked a little about this. We talked a little about how to go about the simplification process. And what I want to do here today is look at some more operations. Just make sure you guys are okay with simplifying, manipulating, and combining terms if we need to. And one of the things that we did discuss last time is this idea of like terms, or like radicals. You gotta be really, really careful when you're combining radicals. You can't combine two different radicals, otherwise, boom, things can explode. It's like adding two different currents, DC, AC, things can happen, so you're gonna be a little careful there. And if I had something along the lines of 2 root x and 7 root x, I can combine this, but I probably want to use some properties of exponents first. And one of the properties of exponents, again, is if I have a times b raised to the nth power, this is going to say a to the n, b to the n. And because square roots, cube roots, all the different roots can be written in terms of exponents, that means right here, if I take the root, where it's a square root, cube root, or whatever, AB, I can take it and I can rewrite it just like that. Now, also, if I have AB to the nth power, properties of exponents dictates that I can write this as a to the n, b to the n. Consequently, if I take the square root of a over b, I can take this and I can rewrite it as the square root of a over the square root of b. And sometimes this might be a way that you want to go about this. How you go about your simplification again, you can do whatever you want, however you want, as long as you don't violate any rules of mathematics. You can use property 1 or property 2 and these rules of exponents really however you want to. Now, up here, you can take it and you can rewrite it as square root 2 square root x. You can take it and you can break it apart. Be very careful. What we have here is a product. It's not a sum. It's not a difference. It's a product. And when I have a product, I can use this property right here. It states when you have a product, you can take it and pull it apart like such. And I see I can factor out the root x. Same thing here. So when I take it and I pull it out, I'm left with a root 2 plus 7 root x. I can't do anything here. I'm pretty much stuck, but I was able to at least factor out the root x. It's just, I just can't combine this. Nothing is going to really be any benefit. If I was to have something along the lines of x and then x, then y, again, all I can really do is take this, break it apart, factor out this root x, and I really can't do anything with that root y. So the property that you might think you can do is you might think, okay, it's just make it under a single radical, but that's not how this is going to work. This is a real common mistake you got to watch out for. So once again, you can take it and you can break it in terms of a product. If you're multiplying and if you're dividing, you can turn it into a division problem. Just be really careful. So here's a common error that I see quite a bit on exams and quizzes. And the error is this. Suppose if I have a squared plus b squared square root. The common error that people do is they get things confused. They say, okay, I know something about square roots and squares. Whenever you take the square root, you think that this is going to be this. Because you think you're going to take the square root of the first term and the square root of the next term. But that at all is not how this works again. Well, why not? Well, one reason is whenever I take the square root, have a product, I can take it and I can pull it apart. Another reason is if I was going to look at the square root, what if I was going to take it and rewrite it to the 1/2 power? And let's say for a second it does equal this a plus b. Let's play a big game of what if. What if I came through here and then squared both sides? Using properties of exponents, I know I'm going to have 2 times 1/2, which is 1. But what happens on the right? What happens when I have a binomial and I power it up to the second power? Is that simply a squared plus b squared? No. You also have that 2ab right there. And if you were to simplify down, that's only going to be the case if a and b or one of them is going to be 0. So this right here, you can't do this in general. So be very careful with that. And what I want to do here is I just want to go ahead and do some operations. So I'm going to expand out, I'm going to multiply, add like terms, whatever the problem's asking me to do here. And the first thing I note here is I can expand out. I'll have root 2 times a root 5. And here I'll have a root 2 times a root 8. This piece here, I can take this piece and I can recalibrate it using that property again. If I take the square root of AB, I can take it and I can rewrite it as root A times root B. Guys, if I can make it, I can break it. The property goes 2 different ways. It's not a one-way street. So if I have a root 2 times a root 5, if I have this, I can write it just like that. This is for real values, though. If I jump out of this thing called real values, things change up. We'll talk about that later on. So this part here, I can rewrite this as root 10. This part here, I can write this as 2 times 8, which gives me 16. Then I see 16 is going to be a perfect square. I take 4 times it by 4, I get 16. So I can take this and I can rewrite it as root 10 plus 4. All right, now That's not the only way I can work this problem. There's lots of ways how I can work the problem again. Just make sure whenever you work it, you don't violate any rules of mathematics. And another approach you could take here is you go ahead and simplify the root 8 to begin with. That's going to be 2 root 2. 8 again is going to be 4 times 2. You take the square root of 4 is 2. This 2 is left over. And what's a root 2 times a root 2? It's not 4. It's just going to be 2. And 2 times 2 gets you back to 4. So just two different approaches of how you can go about your simplification. And suppose I want to take this and I want to expand out. Well, how would I do that? Just go and FOIL it out. You do the first, outer, inner, then last. So take a root 7 times a root 7, and then multiply it by the root 5, root 3, root 7, and then by the root 5. So although we don't have things like x plus 2y and 3x plus 5, it works exactly the same way. You have a root 7 times a negative root 5. Then I'll have a root 3 times a root 7, followed by a root 3 negative root 5. So after I have it completely expand out, then maybe want to clean it up a little bit more. And I see here I'll have a 7. Here I can factor out the negative. And I really want to ask myself, is there any kind of simplification that I can do at this stage? And if there is, go ahead and do it. If not, go ahead and move on to the next part of the problem. Okay, so here I'm going to have a root 35. 3 and 7, there's no common terms here. And likewise for the last one. And that's all I can do. I cannot combine this radical with that radical. I can't do it. Again, you have to look forward to see if they're going to be like radicals. And it's just like saying, are they going to be like terms? Okay. Well, let's take the problem. Let's change it up a little bit more. Let's say if I have root 5, root 3, root 5, minus root 3. Let's go and expand out. Well, I can take the root 5 times the root 5, and that would get me 5. You can take a root 5, negative root 3, and put together negative root 15. And then you have a root 3 and a root 5. And then lastly, you're going to have a root 3 times a negative root 3, which is going to get you 3. Well, right here, you can simplify it down a little more, because that is going to be your like radicals. And in fact, this is going to negate. This is going to zero out. And you get a value of 2. Again, there's lots of times just not one way to work a problem. What else do you see here that can make the problem a little faster, a little bit easier? What I see here is the same thing right here and right there, as well as here and here. What's the only difference? One has a difference. Where have you seen this before? Something that's been factored like that. The whole entire difference of squares identity. If I remember the difference of squares identity, I'm going to speed this calculation up substantially. So instead of going through all of this, I would just remember that it's going to be a squared, and if I square root 5, I get 5. subtracted off b squared. And here's my b. If I square that, I get 3, thereby giving us 2 in the very end. Two ways if I can go about this. I can go about the long way, and that's fine. You can take it and you can rewrite it. You can go ahead and expand out and work the problem that way. That's option 1. Option 2 is to start seeing things from a different perspective. Option 2, you're going to see the binomial. You're going to have the a plus b quantity squared, and you know you can take it and you can rewrite it as such. Take the first term, square it, 2 times the first term, the next term, and the last term, square it. And from here, we can do a little bit more of a cleanup job. Of course, we'll have 3 and 8, which gives us 11. We'll have a root 3, and we're going to have a root 8. Now, look before you leap. You can always make a problem more complicated than it really needs to be. My objective is to simplify, and a good rule of thumb is to simplify as you go about the problem. So I have an option. I can take a number and I can blow it out of proportions, make it as big as I want, and then simplify it down, make it smaller. The other option is make the number smaller, then multiply it just a little bit more. The choice is yours. Here's what I can do. I can say square root 24, but then I got to think about how that's going to reduce down. And we're going to have 4 and a 6, so I have a root 4 gets me 2, and I can't do anything with the 6, so we're pretty much locked in place. 2 times 2, of course, this gives us a value of 4. The route that I probably would have taken would be a little bit easier. I would have gone ahead and said 11 to begin with 8 and 3. But I know something about 8, the square root of 8. That's going to be 2 times root 2. And if you simplify as you go, you're going to have smaller numbers. Would you rather work with smaller numbers or larger numbers? It's really your choice. I prefer to make problems as easy as I possibly can and not make them more challenging than they have to be. So by reducing it down, I use smaller numbers. I have 2 times 2 gives me 4. Multiply it, and we get our value of 6. And I can see, okay, there's probably no more things I can do here in terms of simplification, because I did a lot of simplification to begin with. So the choice is like this. You can forget about the simplification, blow the number up, make it big. In this case, it's not that much of a big deal, but some numbers will become a really big deal, where it becomes really big and it's really hard to work. Or you can go ahead and say, okay, let's do a little bit of simplification, make the number a little bit smaller, so that when it comes time to get to the final answer, there's less or no simplification I'm going to need to do in the end because I already did at the very beginning. All right, so just 2 different approaches here of how you can go about the simplification. Even if I have square root x, it's going to work exactly the same way. It's just going to be having square root of x floating throughout the problem. Now, when I look at the problem, I got to ask myself, do I see any kind of formula, any kind of identity that I can use to help me out? Not at first. So I'm going to have this piece times this piece. So 3 times 2, 6. Root x times root x. 5. 1 and the 2. And the 1 and the 5. And this piece here, of course, we can reduce this down. And what happens there? You got your like terms. So we're going to have 17 root x plus 5. Here's the next question. Is there anything that I can do to reduce it down further? Not really. Well, at first, it looks intimidating, doesn't it? You got multiplication, you have these radicals, you have these variables now. But what do you see that can help you in the process? I see how these things are so very close. What's the distinction between the factors? One's positive, one's negative. And when I see this, I jump for joy because I have a pretty good idea how to speed through this calculation, because I know something called the difference of squares and how it factors. So I know the end game, so instead of expanding it out, go to the end game. Take it and plug it in. What did I do wrong? I got to square this as well. So I just can't not square that piece. I also have to square that piece. So 2 squared, 4, then x, followed by y. Let's crank it up a little bit more. Try that one. Take this, expand out, and completely simplify it. Here's some pretty good conversations out here. Let's take a quick look at it. So one thing that I could do when I'm looking at this problem, I can expand out. I can do this. Oh my goodness, that's too hard. It does work though, but I'm gonna burn up a lot of time. So what I need to do is start training myself to look at a problem, ask myself, I see what I might be able to do, and I see that it's going to be a little bit complicated. Am I willing to invest the time required to go through that process? Well, I really don't want to invest the time on this, especially if it's on an exam. So I want to find a way to make this a little faster. What I could do is look at the terms and see if I can find some kind of pattern that's going to help me in an endeavor. I can group these two terms together. And if I group those two terms together, I have the exact same thing right here as I do right there. And what I have here is the same thing here with a difference of a sign. And when I see that, what can I use? The difference of squares identity. So instead of going through that long, drawn-out process, root 2 times this, root 3 times this, look for the patterns, look for something to make this a little bit easier, jump on it. A squared minus your b squared. Now guys, I'd rather work the problem like this than the way I did a moment ago. Much cleaner, much faster. So, start looking for the patterns as you go through the problem. Here's another pattern. Binomial, to which I'm going to square. I know exactly how this is going to expand out. Take the first term, square it. 2 times the second term and the first term together, and the second term squared. If I take a root 6 and I square it, I get 6. Here I get 4, 2, root 6, 3, 7, minus 6, 1. Well, that's cool. I didn't know you could do that in math. Group things around, find patterns to help you out. Absolutely. Oh, I think we're off here. All right, 2 minus. There we go. Good. So, what if I was going to take the problem and tweak it more? We'll put an x here, a y here, x, and a y. What would you do? You can take one term, multiply it out, and get 9 terms again. Or slow down, look for the patterns, apply difference to squares identity, and just start cranking it out from here. Okay, now, questions. All right, so we have a pretty good idea now of how to add, how to subtract, and how to multiply these radicals. What comes next? Divide radicals. That almost seems like a bad joke, doesn't it? How do you divide radicals? I guess very carefully. Let's say if I have 1 over root 2. And when I'm dividing radicals, what I'm looking for when I'm going about this process is a process known as rationalization. It all seems like another bad joke, doesn't it? How do you rationalize a radical? Well, you can't because they're radical. Otherwise, it wouldn't be, rational, irrational. All right. I think about these things too much, I guess. But here's the objective, here's the goal. You don't want a radical underneath you. You want to bring it to the light of day. The question is, how am I going to do this? And the answer is, it depends upon the radical that you're dealing with. So the objective is make this so that I'm not going to have a radical right there. So I need to multiply this by something. Now, I just can't come here and multiply this 1 over root 2 by whatever I want. I can be a little bit strategic about it. And I just can't multiply it by 3 because it changes the problem up. So I need to multiply it by 1, and I can say 3 over 3, because 3 over 3 is going to be 1. But that's not going to help. If I take it and rewrite it in the exponential notation, it becomes a lot more obvious as to what we're going to do. So I need to multiply it by 2 to some particular power so that I will get 2 to the first. And the way that I multiply fractions is I multiply straight across. So I'll have 2 to the power of half times 2 to the power of x. And if they have the exact same base, I add them up. So my equation then is a half plus x equals 1. So in this case, x is going to have to be a half. So if I have 1 over root 2, I can multiply it by a root 2 over root 2, in other words. And a root 2 times a root 2 gets me simply 2. We have just rationalized. All right, so that's not really a big deal. I think we're okay with that. So why am I making this a big deal? How do you rationalize 1 over the cube root of 2? And this is where most students go sideways now. And what they do is this. They're going to say a root 3 over root 3, and this would be a root 3, a cube root of 3 of 2. The common mistake. What's going on? What's the confusion? Well, I think part of the confusion is this. When students see this sign, they automatically default and call it the same sign you would have right here. It looks very similar, but this is cube root. That's square root. And the way that I rationalize with a cube root is not the same way I rationalize with a square root. I gotta be a little careful. If I was to multiply these two things together, first off, this 2 to the 1/3 is also 2 to the 1/3. Does that equal 1? Does a third plus a third equal 1? No. And I know that I got to get a 2 to the first power. That's my main objective. That's my goal. So 2 to the x, 2 to the x. And I probably don't want to write this in the radical notation. Let's do the exponential notation, because that's going to be a lot more instructive as to how you're going to go through the problem. As you multiply straight across, you see you have a third, 2 to the x, and this is your goal again. That's where you're going. How do you get there? What do you need to do? Well, properties of exponent states same base, you're going to add to get the value of 1. So what do you need for x? 2/3, not a third. Here you would have 1/2 to the 1/3, 2 to the 2/3, and when you multiply straight across, 2 to the 2/3, 2 to the first power, and you can use properties of exponents further and recalibrate it, and you can say the cube root of 4/2. Just another version of it. Okay. Now, let's say if I have root 5, 4, and again, what I want to do here is I want to rationalize. So I might want to go ahead and just write this in exponential notation. And I got to ask myself, what do I need to add to 1/5 to get a value of 1? That's my goal. How do I get there? Look at the fraction, and you can say this right here. Now, it's not saying it's going to be the most simplified form, but it is a valid form, which then we can simplify down if we need to. And we also know we can take 4, and we can reduce that down further. That's 2 squared. Properties of exponents also dictates take this power times this power. But now I have an improper fraction, so that's telling me I can reduce it down even further. And we can do what we did the other day. We have 8/5. We could look for powers of 5, pull them out, or we can go ahead and take it and we can use this idea of fractions, add them up, take it and decouple it. So we have 2 times 2 to the 3/5 over 4. And just to make it a little more radical, we'll have 2 goes in the 4 2 times. And I can take this and I can recalibrate it yet again. 5th root of 8. All right, so there's lots of different ways of how I can rationalize and really go about the problem here of maneuvering it. And I might need to know how to do all different techniques, because what if you have a multiple choice question on this? And they gave you this form, and you thought it was only going to be this form. And if the answer choice says something like none of the above, you might say none of the above and get it wrong. So you got to make sure you can maneuver through the different variations of this. What if I had this right here? How am I going to rationalize this one? Well, let's see. If I try multiplying it by a root 2 and a root 2. Well, I'll get a root 2 on top. Down below, I have a root 2 times a root 2, which is 2, followed by root 2. What happened? Nothing really. So whenever I have 1 over a single number like this, this is a really good strategy. Whenever I have 2 numbers down below, things change up a little bit more. And what do I know about square roots? I know if you square a square root, things are going to go away. I can't just come up here and square this. What I need to do is do a sneak attack. And the way I can do a sneak attack is use the whole entire difference of squares identity yet again. Here I have a plus b, and I'll say a minus b, because I know this. When I expand out, I'll take the first term, square it, take the next term, square it, and then simplify it down. This process, we're using what's called the conjugate. And if I was to give you a little more complex problem, the way that I work it is very, very similar. Take whatever you have, flip the sign. Apply the difference of squares identity, simplify it down to get your answer. All right, guys, you have a great weekend. I will see you next time.
I hope that today's lesson was a positive and an encouraging learning experience, and that you have a better understanding of how to solve these problems. Be sure to set some time there today and throughout the week to review these concepts, to rework these examples so that you're better prepared for the next lesson. If you need anything, just let me know. You're always welcome to send me an email or to stop by during office hours. Until next time, keep up the good work and have a great day.